Hello everyone, welcome to chapter 19, planar kinetics of a rigid body, impulse and momentum. This module is going to discuss the conservation of momentum. Now, the objectives is first to understand the conditions for conservation of linear and angular momentum, which is going to be similar for the ones discussed for a particle. So rigid bodies are going to be similar in that sense. And then we're going to apply the conservation of linear and angular momentum to applications and solve problems. Most of the changes or differences are in the way we apply these equations to solve problems. If you remember, if I have the linear impulse and momentum for a rigid body, mvg, remember we use the velocity at the center of mass, mvg1 plus summation of the impulses equals mvg2. Okay, if it happens that the summation of the impulses is 0, okay, if the sum of all linear impulses is 0, or I have no impulses acting on the system, then this is cancelled and we end up with L1 equals L2. So the linear momentum does not change. Therefore, mvg1 equals mvg2. And this is the conservation of linear momentum. Okay. Now, if I want to do the same for angular momentum, again, I have the equation ig omega 1 plus summation of angular impulses should equal ig omega 2. Again, if the sum of all angular impulses is 0, or I have no angular impulses acting on the system, this is 0, as you can see here, and we end up with hg1 equals hg2. So basically, the conservation of angular momentum is done through this equation, and the conservation of linear momentum is done by the previous equation for mv equals mv. Now, if the initial conditions of the rigid body or the system are known, if these conditions are known, then conservation of momentum is usually used to determine the final linear on angular velocity of an object. What is important here is just to note the second point. This is important. The equation can be applied to any random point A other than G. So here we have it, Ig omega 1 equals Ig omega 2. You can apply it to any point A. It doesn't have to be point G. But if you do that, you're going to have to add R times M times Vg for the center of mass. Okay, because remember, if I have an object that is, let's say I have something like this. I have this rod, this is the center of mass, and it is rotating, and this point O is fixed, and this point will have a velocity Vg. If you take I around G, then Vg will not give you any angular momentum because it is passing through G. But if you are to take if you are going to write the equation H around O, then it will equal to Ig omega 1 plus Ig omega 1 or 2, depending if this is H1 or H2, plus M omega 1 Rg with respect to O, which is basically what we are saying here. So just keep this in mind. If you are taking H at G, it's going to be only Ig omega. If you are taking another point, you have to add MVR. Sorry, this is MVR, not omega. So it's going to be M multiplied by VR. So it's going to be VG times RGO. Okay, so you have to add that part to it. Now, the procedure. First, establish your XYZ frame of reference. Draw the free body diagrams if you need to analyze the problem and to understand what forces are acting. Write the conservation of linear momentum if needed. Okay, so you finished your XYZ with the diagrams. Now, it depends. Do you need conservation of linear momentum or conservation of angular momentum? You're going to do what you need of these. Solve the equations. Okay, and if it happens that you need more equations or you have more unknowns, then go back to kinematic equations to solve any additional unknowns. With that, let's start solving problems. We'll start with the first one. Two solid spheres of radius 3 inch, 2 pounds each. So they are identical. They are mounted at A and B, which are having the same distances from the center, as you can see from the figure. So they are identical. Mounted at A and B on the horizontal rod A bar B bar, which rotates freely about the vertical axis with a counterclockwise angular velocity of 6 radians per second. So this is the initial velocity or angular velocity. The spheres are held in position by a cord which is suddenly cut. So you can see the cord, which is the blue line, was holding them, then it was suddenly cut. Now, the centroidal moment of inertia of the rod and the pivot is IR equals to 0.25. So I have I for the T shape, which is I prime B prime 0.0. Let's call this 0.0. So the moment of inertia for the rod, the T-shaped rod, is given to you. Determine first the angular velocity of the rod after the spheres have moved to positions A prime and B prime. Then find the energy lost due to the plastic impact of the spheres. So between the spheres and the stops at A prime, B prime. We'll come to this part later on. So let's solve the first part. Find the angular velocity of the rod after the spheres have moved to positions A and B prime. Okay. So first thing, let's identify our axes. So I'm gonna say I have this is my X, this is my Y, this is my Z. Now I'm gonna draw my diagram. So for the first case, okay, let's say this is the end. This is the second end. This is the point O, let's call it. Okay. And then I have two masses. This is the first one, and then this is the second one. So what do I have? It was rotating. Remember, it was rotating with a counterclockwise. So I'm looking at this as a top view. I'm looking at a top view. So this was having we're going to call it S for the spheres, and we have MR for the rod. So I'm going to call it MS. This is sphere B, so it's going to be VB1, and this is MS VA1. And the reason I took those two velocities, because these are the velocities if I have a counterclockwise rotation, which in this case is I R omega 1. Okay, so this is what I have. Okay, now this is at the initial position. Now at the final position, it's going to look something like this. So it's going to be the same figure, except that the spheres are going to be located at the ends of the rod. So it's going to be something like this, where this is going to be one of the spheres, A, and then I have here the second sphere, B, something like this. And again, this is the center, O. So now, the velocities are going to be the same thing, except that this is going to be MS VB2 instead of 1. And A is going to be MS VA2. And also I'm going to have angular motion. So this is going to be IR omega 2. Okay. So we have everything shown here at position 1, position 2. So this is initially and this is finally. And you have impulses acting on the system. I don't need to draw that one. The only forces I have are the weight. And these are acting, if you look at this figure, are going to be acting towards the picture. So it's inside the plane. So they do not give me any moments. Also, I have the tension and the cord. They cancel because they are opposite in direction, equal in magnitude. So I have nothing. So in this case, the system is conserved, as you can see. So let's start with calculations that we might need. I know that, keep in mind that I know that velocity of A should equal velocity of B in both cases. So although we say VB1, VA1, they are not necessarily different. They are actually the same in this case. And both are equal to omega times R. Depending if it's position 1 or 2, doesn't matter. In both cases, it's going to be omega R. Okay, so now let's start with the conservation of momentum, and it's going to be around the center. So I'm going to say HO1 should equal to HO2. So let's look at H1. I have two spheres, so I'm going to multiply everything by 2. Okay, I have M to MS. Okay, then remember we said VA, VB are the same, so we're going to call it V sphere 1, okay, times R of the distance between the spheres and the point O. So 2 MVR plus the spheres are also rotating, so it's going to be 2 IS omega 1. Plus the rod is also rotating, so I'm going to say IR omega 1. This should equal to exactly the same thing. The only difference is that instead of 1, I'm going to write 2. So it's going to be 2 MS VS2. R is going to change, so it's going to be R2 now, plus 2 IS omega 2 plus I for the rod omega 2. Okay. Now, keep in mind that I also can relate Vs to omega, which is what we said here. Okay. So I'm going to write this as a relation to omega 1. So I'm going to open a bracket. I'm going to have 2 ms. Now V equals to omega R. So I'm going to have R squared. Right? So it's going to be R1 squared because I have one R here and one R coming from V equal omega R. So 2 ms R squared plus 2 I sphere plus IR. All of this multiplied by omega 1. This should equal to the same thing. It's going to be 2 ms R2 squared plus 2 IS plus IR omega 2. Okay. Now let's calculate what I need also. I have IS for the sphere. If you don't know this, it is 2 over 5 M A square. So it's going to be 2 over 5. And I don't have the mass. I have the weight, which is 2 pounds. So it's going to be 2 over 32.2 multiplied by A, which is given to me that the radius is 3 inch of the spheres. Now, since I am writing things in terms of feet, so it's going to be 3 over 12 because 1 feet equals 12 inch. Therefore, 3 inch divided by 12 will give me the number in feet. And this should equal, this is squared, and this will give you a value of 0.00155 pound foot second square. Okay. Also compute any quantities that you might need. I have ms times r1 square. So this equals to, again, I have the weight, so it's going to be 2 over 32.2 square. Okay. So not squares, this is the mass multiplied by r square. Now what is r? R is basically the distance between the center of mass and the center of rotation. Here is the center of mass, here is the center of rotation. The distance is given as 5 inches. So it's going to be 5 again divided by 12 to make it feet square, and this equals 2.015 And I can do the same for the second one, ms r2 square. Okay, now what is the distance? It's going to be the distance at position 2, which is here. This is going to be the center of mass, and this is the center of rotation. The distance given as 25. So again, it's going to be 25 inches over 12 to convert it into feet. And this will equal to 0.2696. Okay. IR is given in the problem directly to you. I for the T-shaped rod will equal to 0.25. Okay. What else is given? Omega 1 was given, I think, in this problem. So it was given at an angular velocity of 6 radians per second. So omega 1 equals 6 radians per second. So this quantity is known, this is known, this is known, this is known, and also these are known. The only unknown is omega 2. So you can solve this equation to give you omega 2 to be equal to 2.08 radians per second. Again, our assumption of counterclockwise was correct. If you got a negative value, that means your assumption is wrong. You have to change the direction. If your assumption is correct, then you got the right direction. Now, the second part, it says find the energy lost due to the plastic impact of the spheres and the stops at A prime, B prime. This is basically, if you are considering the loss, the energy loss, this is basically kinetic energy, the change in the kinetic energy. Let me write the general expression in this problem for the kinetic energy. I have 2 for the spheres, remember. I'm going to have half m sphere, velocity of the sphere square, plus I also have half I for the sphere, omega square. So I have 2 of these. Plus, for the rod, I have only rotation, so it's going to be half IR omega square. Now, regardless if 1 or 2, we are writing this in general. Again, the spheres, they have velocities at their center of mass, and they have also the rotation of the rod that they are mounted on. So they have general plane motion. So they have half mv square plus half I omega square. And then you have for the rod only half IR omega square. So if you write it for T1 and T2, T1 will equal to let me arrange this one also before T1. So we can also write this expression as a general expression for both. We can make it shorter. So it's going to be T equals to half, just do everything in there, of 2 ms r square plus 2 is plus ir omega square. Okay, so this is the short version of that one if you rewrite it. And therefore, let's calculate each one. T1 will equal to half. Now, what do I have here? I have 2, and then ms. Remember, the mass was given as 2, so we have 2 over 32.2 times r, which was 5 inch, so it's 5 over 32.2 square. Okay, plus, so this is for the whole thing, plus 2 multiplied by is, which was equal to, remember, we calculate as 0.00155, so plus 0.00155 plus IR, which is 0.25. All of this multiplied by omega 1 square, which is given as 6 radians per second. So I'm going to delete this one. I'm going to write 6 square. Okay, this is T1, and this will give me that T1 should equal to 4.95 feet pound. Okay. And if you do the same thing for T2, just change the values, you will get T2 equals to 1.713 pound foot, or foot pound is the same thing. Okay. Therefore, the energy loss delta T will equal to T2, because this is the final position, minus T1. And this difference gives me 4.95. Sorry. This will be 1.713 minus 4.95. So energy loss means it's negative, as you can see, 3.24 foot pound. And this solves the problem for you. The second part is basically from the energy and work and energy equations, or potential energy, kinetic energy, but it is related to this problem, so it was interesting to solve it. Now let's look to second problem. The uniform pole has a mass of 15 kilogram and falls from rest when theta equals 90. It strikes the edge at A when theta equals 60. If the pole then begins to pivot around this point, point A. To pivot means to start rotating around A. It's like point A is the center of rotation. So when it starts to pivot around point A, determine the pole's angular velocity after the impact. Assume that the pole does not slip at B and it falls until it strikes A. So for this problem, to understand it, you need to draw 3 diagrams to understand what's going on. The first diagram, position 1, let's call it, is when the rod is vertical like this, and it is rotating around point B. Okay, so it's rotating around point B, and this is the center of mass G. Okay, so it begins to fall. The problem says it begins to fall. That means, so this was 90 degrees, as you can see, and it begins to fall, so it's falling in this direction. Okay, and that's what we have in this problem. So this is the first part. Okay, and you have the weight acting downward. So this is the weight, which is the mass given to me as 15. So this is 15 times 9.81. Okay, now position 2, okay, is basically the rod at an angle of 60. This is point B, and it hits this point A. Okay, and the center of mass is here, G, and this is gravity acting downward, which is 15, 9.81. I'm just drawing the the diagram showing the location of each one. Now, position 2, and then position 3 is going to be almost the same as position 2, but there's a difference that I will discuss right now. Okay. So again, this is point A, and then here the center of gravity G, and you have 15 over times 9.81. Now, what is the difference between 2 and 3? Here, point B is my center of rotation because it was falling from A until it reaches point B. Okay, therefore, it was pivoting around B, so it's like B was my center of rotation. Now, in point 3, once it hits A, it starts to pivot around A. In this case, A is my center of rotation in this case. Okay, so I'm going to delete these. I'm just going to put at A, I have my center of rotation. Okay, so this is the difference between 2 and 3, and this is very important for this problem. Now, the problem is basically a conservation of momentum when it starts to rotate around A. So the pole will hit point A, and then it will start to rotate around A. In that case, the weight is not an impulsive force. It's not going to give me any angular impulses. And the reactions at A cancel, so I have nothing. The system is conserved around A. The only thing that you have to pay attention to in this problem is that the pole was falling from location A. Therefore, I need to solve from location 1 to location 2, and then I will start solving my problem. So first thing, from 1 to 2, it's not an impulse problem. It's actually conservation of energy. Conservation of energy between 1 and 2. So I'm going to pick, first of all, the datum. Datum is at point B always for this problem. So the datum is at B. And the pole was given that it was falling, so therefore nothing was mentioned, no velocity was given to it. So let's start. T1 plus V1 should equal to T2 plus V2. So T1, it was 0, starting from rest, plus potential energy, I have no spring, only the weight. I am above the datum, so I am going to have a positive value. So plus 15 times 9.81 times the distance h. What is the distance in this case? It's the distance between G and the center of mass. The length is 3 meters, so that one becomes 1.5. Okay. Equals to. Now, T2 is unknown, so it's going to be I. It depends where do you want to take it. So do I take it I around the center of mass G or I around B? Now I can take it I at B if I want. Okay, omega 1. So this is optional, and I will come to what is the difference between these two. So it's going to be half IB omega. Sorry, forgot the half in there. So it's going to be half I around B omega 2 square plus the potential energy. Again, I am above the datum, so it's going to be 15 times 9.81 times what is the length in this case. Let's look here. So now at position 2, my center of mass is located here. So I need this distance. Okay, if this is 1.5 and the angle is 60, then I end up with, you have, this is 1.5, this is 60. So if you take sine 60, it will give you this length, or let's call it h, over 1.5, and then you multiply it by 1.5. So it's going to be 1.5 sine 60. So this is multiplied by 1.5 sine 60. Now, IB, I'm going to do it separately on the side. You have two options in this problem. Either to do I at G and include the velocity of center of mass G, but I want to eliminate too many unknowns and try to solve them together. So I'm going to do I around B, parallel axis theorem. So I have 1 over 12, the mass, which is 15, times the length, which is 3 square. So 1 over 12 ml square plus md square, which is in this case m is 15, and d is the distance between the center of mass and center of rotation, which is in this case 1.5. So go back to your parallel axis theorem if you're not sure about this, and you can review it to know how to apply it here. This will give me 45 kilogram meter square. If you didn't want to do this, I'm just going to put this in a box here. If you want to do it around G, So in that case, you have to do, in that case, T2 will equal to half m Vg square plus half Ig omega 2 square. So either you do it like this or you do it like this. Actually, this is a good practice. Try to do it this one by yourself and see if you get the same final answer that we are going to get. Okay, so you have everything in there now. If you substitute everything back into the equation, it will give you that omega 2 comes down to be equal to 1.146 radians per second. Still, I did not solve conservation of momentum. That's what I'm going to solve right now. Okay. Now, let's look at the problem between 2 and 3. So I'm solving 2 to 3. Okay. What do I have now? First of all, I have conservation of momentum from before and after. Let's calculate G. I'm gonna use it later on, and I'll show you why. So it's gonna be 1/12, the mass, which is 15, the length, which is 3 square, and this equals to 11.25 kilogram meter square. And also, I'm going to calculate I around A. And again, I'm going to show you in a few seconds why I need this. So it's going to be Ig plus M RGA, the distance between the two, which will equal to 11.25 plus the mass, which is 15, okay, times the distance. What is the distance between G and A? It's not that difficult, but you need to pay attention to it. Now, I need the distance. I need this distance. Okay, so first of all, this one is 1.5. We know it already. And this one is basically, you have the angle given to you, and the distance here is given. This is 0.5. Okay, so this distance, I don't know it. I know that this distance, let me draw it here separately. So this is the center of mass G. Let's say this is point A and this is B. And the angle is 60. And this is 0.5. And this is 1.5. So I have 1.5. So the distance between R GA, it's going to be 1.5 minus, what is this part? It's basically 0.5 over sine 60. Why? Because sine 60, let's call this x. Sine 60 will equal to 0.5 over x. Therefore, x equals 0.5 over sine 60. And that's what I'm doing here. So it's going to be 1.5 minus x gives me the remaining distance in here. Okay, so back to my problem. So it's going to be 15 multiplied by 1.5 minus 0.5 sine 60. I'm just going to calculate this, and it comes down to 24.02 kilogram meter square. Now, let's write the conservation of momentum. So it's going to be around point A. So HA1 should equal to HA2. Let's look at HA1. What do I have now? So we're looking at this one. So sorry, I should write it 2 and 3, not to confuse you. So I'm going to write this H2 and H3. Okay, so at H2, at location 2, what do I have now? I have the velocity of the center of mass when it was falling. So let me clear some of these things just to make it clear. So I don't need these any longer. Okay, same thing. We already discussed this, so we know. Okay, so what do I have now at the first one? So this is when the object was rotating around B. Keep in mind, the rod was falling down and it was rotating around B before it hits A. Before it hits A, I'm going to have velocity of G like this. I'm going to have omega 2 like this. So let me write this part first. So I have two components. Okay, so it's going to be the first component M Vg2 times R G and A, the distance between G and A, plus Ig omega 2. This should equal to, now let's look at the second part. Remember, I'm taking the angular conservation of momentum around point A. In location 3 or position 3, it is the same as position 2, but the only difference is that it is now rotating around A instead of rotating around B. So I can say Ig, I can say, Ig omega 3 plus MVG3 and so on, or I can take I around A, which is what I calculated, and I told you that I'm going to use it. So it's going to be I around A omega 3. Again, you might wonder, why didn't I do the same thing for the first part? I'm taking H around A. Keep in mind, this is the secret. H is taking around point A. So when I analyze the problem at position 2, case 2, when I take A, my center of rotation is not the same as the center of conservation of momentum. Therefore, I have to take Vg and I have to take also I omega. In position 3, it happens that point A is the same as the center of rotation. Therefore, I end up with only I omega. That's the difference between the two cases. Let's look at the numbers now, so it might be more clear when we start putting them. So the mass in this case is going to be 15. Okay. Now, velocity of G, I can write it as omega r also. So what is omega 2? Remember omega 2, I can say that Vg2 equals omega 2 times r. And what is this r? It is r, the distance between, let me show it to you, between A, where is it? So it is between G and A, because I have velocity of G, right? And I want to convert it to point A. So it's going to be RGA. So what do I have? Omega 2 equals 1.72. And then R between G and A, we already have it from here. So it's going to be 1.5 minus 0.5 sine 60. Okay, so this is for the first part. Plus Ig equals to 11.25 multiplied by omega, which is 1.146. Okay, so if you go back to this, actually, so omega 2 was 1.146. So this should be 1.146 here. So this is basically, if you calculate Vg from here, Vg equals omega r, and if you calculate it, you will end up with this equals to, I did not calculate this to you, this equals to 1.72. Sorry. Okay, 1.72 meters per second. Okay, and r here is not GA, sorry. Let me clear this one to you first. So, first of all, let's go back here. Vg, this is at position 2. And at position 2, what is my center of rotation? It is point B. Therefore, if I want to relate omega and velocity, V equals omega r. R is between the center of mass and the center of rotation, B, which will be 1.146 multiplied by 1.5. and this will equal to 1.72. I wrote it there because I already have the numbers calculated ahead of time, so I forgot to just show it to you. So this is VG2. Now, the confusion in this problem comes with why am I using RGA instead of GB? Because I'm doing H around point O, therefore velocity G is going to give me an angular momentum around A. So I'm taking VG as it rotates around A. Okay? VG as it rotates around A, therefore I need the distance between G and A. That's why we say MVG, which we calculated, times RGA. This is the one that we have. And then IG omega is straightforward. Equals to, now, since I'm taking H around A, I already have the value calculated. So it's going to be 24.02 multiplied by omega 2, which is unknown, which is what we need to find. 3, afwan. So this is at position 3. If you solve this, you end up with omega 3, equals to 1.53 radians per second. And this solves the problem to you. Again, I just want to clear this issue to you. Let me just, after we solve this, I'm just going to repeat this issue to you so that you understand why we are doing this. Now, let's leave this alone on the side for now, and let's look at the problem. So, first of all, you understand that if I want to find a relation between omega and Vg, it's always omega multiplied by r between the center of mass and center of rotation. Center of mass is G, center of rotation is B, therefore omega 2, which is 1.146, multiplied by the distance 1.5 will give me this value. This is clear. Now, when I want to solve H around point A, okay, so when I wanted to solve H at point A, okay, therefore, what do I have? I have the center of mass is moving. So it's going to be M, the center of mass is moving. Then, since this is angular momentum, the linear momentum, mv, has to be multiplied by the distance to make it similar to force and a moment. Force multiplied by perpendicular distance will give you a moment. Linear momentum multiplied by perpendicular distance will give you angular momentum. So it's mvg, and then to make it angular momentum, it's the distance between G and A. And I have rotation there, so it's going to be I G omega 2. Now, in position 3, I don't need to do the same because my center of rotation is the same as the point I'm doing it there. So I can do it IA omega 3 directly. Another option, if I wanted to do it, would be or. I would say M VG3 R G to A plus IG omega 3. But then you end up having to relate VG3 equals to omega 3 equals omega 3 times R G relative to A. So it becomes lengthy. That's why we use this one instead. So with this, I conclude this problem, and I hope that this module was useful to you, and I wish you the best of luck. Thank you.